Have you ever looked out the window during a road trip and noticed those giant steel towers marching across the landscape? They're everywhere, crossing fields, climbing hills, and stretching toward the horizon. Most of us barely pay attention to them, but once you stop and really look, a question pops into your mind. Why are power line towers shaped like that? Why do they look like giant metal skeletons? Why aren't they solid poles or simple columns? And why do some of them have those wide arms sticking out from the sides? As it turns out, their unusual design isn't just for looks. Every angle, every beam, and every piece of steel serves a purpose. So, let's break it down, right here, on History of Simple Things. In the early days of electricity during the late 1800s, power stations supplied electricity only to nearby areas. As electrical demand grew, engineers needed a way to move electricity much farther from where it was generated. One of the pioneers of long-distance transmission was engineer and inventor Mikhail Dobrovolsky, whose work with alternating current helped make high-voltage transmission practical. By the early 1900s, countries around the world began constructing large transmission networks. Wooden poles worked for shorter distances, but as voltages increased and transmission spans became longer, stronger structures were needed. Steel lattice towers emerged as the preferred solution because they were durable, lightweight, and capable of supporting heavy power lines over great distances. The familiar tower shape we see today evolved gradually through decades of engineering improvements. At first glance, a solid steel tower might seem stronger than one made from hundreds of interconnected metal bars. Surprisingly, that's not true. Power line towers use what's known as a lattice structure. This design distributes forces throughout the entire framework. Instead of relying on one massive piece of steel, the load is shared among many smaller components. Think about a bicycle frame. It looks light and thin, yet it's incredibly strong because its triangular arrangement spreads forces efficiently. Power line towers work on the same principle. A solid tower would require far more steel, making it heavier, more expensive, and harder to transport and construct. The lattice design achieves nearly the same strength while using significantly less material. If you look closely at a transmission tower, you'll notice one shape repeated everywhere: triangles. Engineers love triangles because they're naturally rigid. Unlike squares or rectangles, triangles don't easily deform when forces are applied. Imagine pushing on the corner of a square made from sticks. It can collapse into a diamond shape, but a triangle holds its shape unless one of its sides actually bends or breaks. Since transmission towers face strong winds, changing temperatures, and the constant weight of power lines, engineers use thousands of triangular sections to create a structure that remains stable under challenging conditions. This is one reason why these towers can stand for decades with relatively little maintenance. Those horizontal arms extending from the tower are called crossarms, and they serve an important purpose. High-voltage electricity can jump through the air if conductors get too close together. This phenomenon, known as electrical arcing, becomes more likely as voltage increases. To prevent this, power lines must be spaced far apart. The crossarms provide the necessary separation between conductors while keeping everything supported safely. The exact width depends on the voltage being transmitted. Higher voltages require greater distances between wires. That's why some towers appear much wider than others. They're often carrying electricity at different voltage levels. Power line towers don't have an easy job. They're exposed to nature 24 hours a day, every day of the year. Strong winds can push against both the tower and the wires. Heavy rain, ice accumulation, earthquakes, and even extreme heat can place additional stress on the structure. The tower's open lattice design actually helps reduce wind resistance. Instead of acting like a giant sail, air can pass through the gaps in the framework. This greatly reduces the forces acting on the tower during storms. A solid structure of the same size would experience much higher wind loads and would need substantially more material to remain stable. The height of transmission towers isn't arbitrary. Power lines must remain safely above roads, buildings, trees, and people. They also sag naturally under their own weight, especially during hot weather when metal expands. Engineers carefully calculate how much a line might sag under various conditions and then design towers tall enough to maintain safe clearances. The greater the distance between towers, the more the wires tend to droop. Taller towers help compensate for this effect while allowing electricity to travel efficiently across long distances. The next time you see a power line tower, you'll know there's much more to it than meets the eye. Its distinctive shape isn't the result of aesthetics or tradition. It's the product of generations of engineering aimed at solving a difficult challenge, moving enormous amounts of electricity safely across vast distances. The lattice structure saves material while maximizing strength. The triangles provide stability. The wide arms keep high-voltage wires safely separated. And the open framework helps the tower withstand decades of wind and weather. What looks like a giant metal skeleton is actually one of the most efficient structures humans have ever designed, a silent but essential part of the electrical network that powers our modern world. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.